Today I want to talk about section 7.3. It's called Sum and Difference of Complex Numbers. Basically, what we're dealing with is imaginary numbers. You've seen these before back in Algebra 2. We know I is the definition, or what it is it's equal to the square root of -1. Okay. What it does is it helps us solve problems like x squared plus 1 equals 0 or x squared equals -1. It helps us solve problems like that otherwise would have no solution. And they don't have any real solutions, but they do have imaginary solutions. Okay. So basically, what I does, just a little reminder, it helps us simplify problems like the square root of -9. We know the square root of -9, or square root of 9 is 3. So the square root of -9 would be 3i, okay? And we can simplify problems like the square root of 24. We break it down into its prime factors, 2 and 12, 2 and 6, 2 and 3. So we have a pair of 2's, we can pull a 2 out. We have a 2 and a 3, so we have that 6 left inside. And then the negative, we just put an I there. So that would be 2i root 6. And we write our answer like this instead of putting the I at the end, because if we put the I at the end, it can get confusing, is that I underneath that square root or not? So we try not to write it like this. It's a lot more clear when we write it like that, okay? Same thing with something like this. Square root of -72. 72 breaks down into 2 and 36. We know 36 is 6 and 6. So we can pull out a pair of 6's. We have a 2 stuck still inside. Because of the negative, we have an I, and we're done. Okay, so these are problems that I think you've done in the past, but we can use imaginary numbers to do that. What a complex number actually is any number that can be written in this form, this a plus bi. Okay, this is what is known as a complex number. Okay, where a and b are real numbers. Complex numbers, basically. All numbers are complex numbers, even real numbers, numbers we've dealt with in the past, because basically the I could be 0 or the B could be 0, which means you only have a real part. And basically in a complex number, it has two parts. In the A plus BI, it has a real part and it has an imaginary part. Okay, so when we start looking at what makes up complex numbers, they can be just real numbers. If their B is 0 and all you have is A, well, then we have all the numbers that we've dealt with our whole lives. We have, real numbers. Inside of that, rational, integers, whole numbers, all that good stuff. We have irrational numbers. These are all examples of complex numbers. But if B is anything other than 0, we have imaginary numbers. We have numbers like 2 plus 3i. That's an imaginary number. 4 minus 5i. This number is a complex number. That's an imaginary number. Okay. 6 plus I. That's a complex imaginary number. We have what are called pure imaginary numbers as well, where there isn't a real part, right? The a would be 0, and we end up with numbers like 3i or 2i or -4i. Okay. So we have these different types of complex numbers, and it really just boils down to this. We have any number like a plus bi. All complex numbers will have a real portion, and they will have an imaginary portion, okay? All right, so let's try some things with these. Well, before we really get into more of the A plus BI stuff, we talked about this earlier in the year because I wanted to make sure you hit this before the SAT. So I remember we talked about it earlier this year, but I wanted to revisit this in more detail, okay? When you start dealing with I to powers, these actually are really easy to simplify, because if you find the pattern, where you say I to the first power, well, that's just equal to I, okay? Well, I squared, that's the same thing as I times I. Well, I times I is the same thing as the square root of -1 times the square root of -1. And we know that the square root of any number times the square root of itself, when you multiply numbers like the square root of 3 times square root of 3, the square roots just end up canceling, and you end up with -1. Okay? Which means if we take I to the third, which is I times I times I, well, two of these together is going to make -1. So then we just have this I, so that's going to be -I. So I to the third power is -I. And then if you keep going, I to the fourth, well, that means it's I times I times I times I. These two are going to make -1. These two are going to make -1. Multiply those together, you end up with a +1. So the pattern goes I, -1, -I, back to 1, which means if you keep going I to the fifth, 1, 2, 3, 4, 5, these four i's are going to make a +1 times I. You're going to basically start back over with this pattern. So this pattern here is basically just going to repeat itself. I to the sixth would be the same thing as I squared, or -1, okay, and so on and so on. So to figure out where I to the 18th power is, all we got to do is figure out where in this pattern does I to the 18th land. And there's an actual really, really easy way to figure this out. All you have to do is do 18 divided by 4. That's it. Why 4? Because there's 4 numbers in the pattern. If you see a remainder of 1, okay, 1 out of 4, meaning 0.25, well, that means we have a remainder of 1, and the answer is going to be I. If you see a remainder of 2, or 0.5, that means you have a remainder of 2. The answer is going to be -1. If you see a remainder of 3/4, or 0.75, you have a remainder of 3. That means the answer is -1. And if you have no remainder, goes in 4 out of 4 times, okay, then the answer is just going to be 1. So there's a very, very easy way to do these. You just grab any basic calculator and just divide the exponent. So 18 divided by 4 is 4.5. Now, we don't actually care about the 4. All we care about is that 0.5. Since we see a 0.5, we know there's a remainder of 2. The answer is -1. You're done. And you can do any number that way. I to the 234th. It's just a matter of doing 223. Divide that by 4. We see a remainder of 0.75. A remainder of 0.75 tells us there's a remainder of 3. It's the same as I to the third, which is -I. We can do I to the 432nd. We just take 432. We divide it by 4. We see the remainder is no remainder, which tells me that's the same as I to the fourth, which is equal to a +1. You can do I to the 1,237th power. You just simply divide that by 4. We check the remainder. We don't care about the 309. We only care about that 0.25 there. The remainder of 0.25 tells me there's a remainder of 1/4, which is the same as just a +I. Okay? So those are some easy ways to do some simplification type things with imaginary numbers. But title of the subject was to add and subtract complex numbers. This is as easy as it really gets. If you just remember there's a real part, here's my real part, here's my real part over here, here's my imaginary part, here's my imaginary part. This is exactly like you think it should be. You're just combining like terms. You combine the real portions, the 3 and the 5 make 8. You combine the imaginary parts, 2i, 7i is 9i. You're done. It really is that simple. It's just like they were x's. It's just you're just combining like terms. You have a real part minus a -7 real part. 11 minus a -7 would be the same as 11 plus 7, or 18. 5i minus a -6i would be a positive 11i. You're done. You're just combining like terms. Sometimes you got to simplify before you can get to that point, though. You take something like we just did before. I to the 9th. Well, if you take 9 divided by 4, you're going to see a remainder, right? 9 divided by 4 has a remainder of 0.25, which means the same as 1/4. So this is the same as 1i. So this is the same thing as 9 plus a single I, plus 6 minus 3 times I to the 3rd. Well, we already know I to the 3rd. If you remember, I'll pull that back. I to the 3rd is the same as -I, right? So that's the same thing as a -I there, which turns that really into a 6 plus 3i, right? And then again, you're just combining like terms. So 9 plus 6 is 15. I plus 3i is 4i. And you're done. So this is not one of the more difficult sections to do some of the practice. The biggest thing is to kind of understand really what we're dealing with here with these imaginary numbers. They're called imaginary numbers because they're not real numbers, right? It's how they came up with that name. What's the opposite of real? It's imaginary. But they do allow us to solve some problems that otherwise are unsolvable, kind of thing. So we will do some more with complex numbers in the next couple sections. But in the meantime, try a few problems. Let me know if you have any questions, okay? Let's finish strong this year. We're almost done. Just a couple more seconds.